Welcome to part 4 of the walkthrough tutorial for Digital Dynamics Studio. In this part today, we're going to actually be running our simulation of airflow past the cylinder. If you remember from the previous part 3 of the walkthrough tutorial, we loaded the model into the simulation tab. We created our initial mesh, which is what we're seeing here. We set up our simulation parameters the way we want them to be. We want to simulate a condition of airflow past a cylinder of Reynolds number 400, and the viscosity that we set will allow, the correct value for Reynolds number 400. The airflow, the way we set up the boundary conditions is that the airflow will be coming in on the left through the left boundary, leaving on the right boundary. The tops and the bottom boundaries will just stop the fluid from penetrating those boundaries, but allow it to slide along those boundaries. And we have a no slip condition on the cylinder itself. So those are all represented in the boundary conditions that we set up in the last tutorial, part 3. But in part 4 today, we're ready to run the simulation and generate simulation frames. But before we go ahead and do that, we want to quickly review a few things of what's going to happen when we actually run the simulation. The first thing we want to note is that the simulation is going to run locally on your computer. If you're on a desktop or a notebook or a tablet, your processor, your computer is going to be running the simulation. It's not going to be running in the background in the cloud or on a server somewhere. Your computer is going to be used to run the simulation. And since each computer has a different speed and different processing power, some systems might run the simulation very fast, can generate a lot of frames in a short amount of time, and some weaker systems like a tablet or something might take longer to calculate the same simulation and just would be slower. It's just a slower processor. So it might take more time. So just be aware of that. If you're using a faster computer, it will run the simulation faster. If you're using a slower computer, it'll take a little bit more time to run the simulation. But the key thing is that it's going to be running locally on your computer, not in the background or in the cloud. The second thing to note is that most processors, as most people know, are composed of multiple cores, and each core is kind of a separate processing unit on a processor. Very common to have at least 2 cores. 4 cores on a processor, very common even on tablet devices. 8 or 16 cores are even possible on notebooks or desktops, even larger in some cases. But so that a digital dynamic simulation engine will be using multiple cores, multiple threads to run the simulation on your system. It'll go up to 4 threads, and it'll assign a thread to each core. If your system supports it, if your system only supports 2 cores, it'll use 2 or 3. If your system only has 1 processor, or it doesn't allow the browser to use multiple cores, it'll just use 1. It'll run slower, but it'll still run. But in those cases, it'll be using multiple processors, multiple cores to run the simulation. And of course, the benefit is it'll be able to run the simulation faster by using more cores. As more processing power it can leverage, and it would run the simulation faster if it's using more cores. So that's another thing that's happening behind the scenes on your processor when it runs the simulation. The third thing to note is actually what's going to happen. As we said before, it calculates multiple frames in a simulation, and and these frames are separated in time by a distinct time step size, which is what we said here. Kind of like a movie where, a movie is a collection of still images separated by a small time step. And when you play them back, you see the movie, you see the animation, you see things flowing nicely. It's exactly the same here. We're calculating the solution, the fluid flow solution, based on the governing equations, at distinct intervals in time. Minimal, probably 500 time steps or frames are common. 1,000 to 2,000 are very typical in a simulation. You can run it for 3,000, 4,000 if you want, but basically you run the simulation as long as you want until you get the result that you're looking for. Maybe things start repeating themselves and there's no point going further, or what you wanted to analyze and the results have happened and you have enough frames to capture that. So at some point you're going to stop the simulation, but typically, like I said, anywhere between 500 and 2,000 frames are very common. So that's what's going to happen when we run the simulation. And finally, we want to note that as these frames are being computed in your simulation, they're going to be saved and cached internally within the browser. We want to save those frames. We don't want frame 500 deleted when we compute frame 501, and we don't want that frame deleted when we compute frame 502. We want them saved internally so we can play it back and go back in time and review our results. So the browser is going to cache all those frames, all that data internally in your browser. And your browser is going to do what it's going to do. Maybe it'll keep it in memory, maybe it'll write it to disk. Your browser is managing all that, and behind the scenes, you don't even know that it's happening, but all the simulation frames are cached internally as they're being generated. So that's the final thing we want to note before we actually run our simulation here. Okay, we're ready to go. To run the simulation, you push this button down here, the person standing. And that means it's either the simulation hasn't started yet or it's paused. But when we click on that button, the simulation will begin. And there it goes. So you can see here, the timeline is advancing as frames are being computed. It's doing a pretty good job. They're computed very fast in this particular setup. We're at frame 500, 600, 700, 800. You see it advancing, and you see the results updating in the screen as that's happening. You can pause the simulation anytime by clicking on that icon again. So now it's in the paused state. You can restart the simulation by clicking it again. You see the timeline advancing. You can pause it, advance it, whatever you want to do. You can still fully interact with the application as it's running. You can even switch tabs up here if you want to. It keeps running. So it's all happening in the background on your computer, so you can still fully interact with the apps. Let me just pause the tutorial here for a moment and talk about the playback rate of the simulation results that you're seeing here on the screen. We just want to note that the tutorial recording software isn't doing a good job keeping up to date with how fast these simulation results are updating in the browser. Probably to you, it looks very jerky and very not doing a very good job, but that's just the fault of the recording software that we're using for recording tutorials. What we're showing here on the screen is what you probably will actually see in your browser, the rate that things are updating and how smooth everything looks with the results. Like I said, it's just the fault of the recording media that we're using for this tutorial, which is kind of making things look jerky. It just can't keep up to speed with the software itself. So what you're seeing on the screen here are velocity vectors and how fast. This is normally what you would see in the browser when you're either running the simulation or especially playing back the simulation. You'll see a rate like this. And here's the mesh, how the mesh is updating. You should normally see this kind of playback rate when you're playing back your simulation results. So we just wanted to pause the tutorial here for a moment and just briefly mention that the recording media is just not doing a good job of keeping up to date with how fast these simulation results are updating. So we just want to note that, and we'll go back to the tutorial right now. Thanks. Well, one other thing we want to note is that as the simulation is running, you can't change your simulation parameters. They're kind of locked in stone. Once you start the simulation, you can review them, you can see them, but you can't change them anymore. As you can see here, everything's disabled. If you did want to change them, maybe you want to do a different Reynolds number, you want to change the viscosity. You can reset your simulation at any time by clicking on the X button here. And when we do that, it deletes all the frames that were cached. They're deleted from memory, from disk. And you kind of go back to the way you were at the beginning. You have your initial mesh again. You're ready to go for a new simulation. And you can edit these values again. You can change the parameters if you want. And you restart the simulation by just starting it again, pushing the standing person icon again. And now the simulation is running again from the beginning. And you can again see that the simulation parameters have been disabled. You can't change them while the simulation is progressing. So let's close that window here. So let's let the simulation run for a little while. We're at frame about 1,000 right here. 1,100, you can see that it's progressing over time. Okay, let's pause the simulation and look at our playback controls. So these are the playback controls here on the left. As if you remember, we stated that each of the frames, again, we have maybe 1,200 frames here. They have been cached internally and are still there. So at any time, we can pause the simulation and play it back using these controls over here. So you can see here, it's not computing them from scratch, it's playing them from the cache. So in general, it'll play it, might have been a little bit slow to run your simulation on some systems, but if you play it back from cache, it should play them back at a much faster rate, a very interactive, very fluid flow, a very nice rate as we see here. You can, play it from cache, pause it, play it. You can step backwards frame by frame by pushing this button here on the left. On the right, you can go forward frame by frame. You could hold the button down and it kind of plays it, keeps going at a much slower rate. You can even use the left and right arrow keys on your keyboard to do the same thing, to go backwards and forwards in time, like we see here. This button jumps to the beginning, this one jumps to the end, the last frame that you've computed. You could continue the simulation again. But yeah, note this button here. This is the track latest frame. If it's enabled, that means your display is updating as the results are being generated. You're always seeing the latest frame. But if you push that button, you're not tracking the latest frame. It's stopped at frame 2240. But you can see it's still computing the frames. Still, the simulation is running, but you're not seeing the latest frame. You can click that again, and you'll see the latest frames. We stop it. Your simulation is still running, but you're not seeing the latest frames. You can even play it back while the simulation is running. You can, inspect the data even as the simulation is running. But this is the track latest frame button, and again, you can enable that, and you will be tracking the latest frame. So that's another little helpful feature there as well. And we talked about this briefly. This is the movie making button. That's going to be the topic of tutorial 6. We'll talk about that more in that tutorial, but this allows you to play back your animation once you have your flow visualization variable set up and record an MPEG movie of your results and download them to share with others or use in a presentation or however you want to do it. So we completed a bunch of frames and now we're playing it back, the simulation. You can see that after a while, you can see here the vortex jetting phenomena that's happening behind the cylinder. We're going to talk more about visualization in part 5 of the walkthrough tutorial. But you can see it kind of repeats itself over time, by letting the simulation progress further. You're not calculating anything new. So we could have stopped the simulation here. You can see the timeline. The total number of frames is shown on the extent of the timeline to the right. And the darker blue is showing what we're seeing on the screen. So we're seeing on the screen about frame 2000. In theory, we could have stopped the simulation here and we would have had all the results that we needed. But you can see when you're playing back what we're seeing on the screen, you can see the dark blue extent of the timeline shows you what you're currently seeing on the screen. And you can pause it again, step forward and back, and you can see how that the dark blue part changes as you progress. So we didn't have to run the simulation this long. We ran it pretty far, but we could have stopped it maybe around 2000 or so and had all the results that we needed, because after that point it just kind of repeats itself over and over again. So we're not going to talk too much about the display parameters. We're going to talk more about those in the next part of the tutorial. But a couple basic things. By default, you're seeing the mesh and velocity vectors. As we said at the last part of the tutorial, all the flow variables are computed at the nodes of the mesh. Those are the corners of the triangles, and the triangles are called elements. So you can see that we calculate velocity at each of the nodes, and we're calculating pressure at each of the nodes. Again, we're going to talk more about that in the next tutorial, but you can see the velocity vectors at each node. They're showing the direction of the flow at each of those locations, and their length denotes the magnitude of the flow at each of those locations. If we zoom in here, you can see some of these velocity vectors are shorter than others, and that just means that the velocity is slower in these locations than at the other locations. But it shows you definitely the direction that the flow is moving at each of these locations. So you can enable that by clicking on this icon and the display parameters. You can just toggle those off. You can turn off the mesh and then look at the velocity vectors alone as we play back our computed animation. And if you go back to look at the mesh, remember we said at last part of the tutorial that the algorithm is an adaptive algorithm, the solution adaptive algorithm, where the mesh structure, the size and shape of the triangles, the elements, the location of the nodes are created and destroyed so that the mesh follows the features of the flow. And that's an advanced technique which ensures accuracy of the solution at each frame. Basically, it's putting the nodes where they're needed the most, where the flow is most complicated. And that's where you need a very dense, higher resolution meshes where the flow is changing or where the variables are changing rapidly. So to ensure accuracy, it is adding nodes and making the mesh finer, smaller triangles, more nodes at those locations where things are happening in the flow. Not much is happening out here, so it's fine. Big triangles, a low density of nodes are fine out here. Not much is happening. Everything is happening around the cylinder and in the wake, and you can see that's where the automatic algorithm is adding all the nodes, all the triangles in those regions, so that it's most accurate to capture those features that are actually changing rather than features that are just not doing anything in these outer regions out here. And this is an advanced technique. The student doesn't have to deal with a mesh, doesn't have to create a mesh. It's all handled internally within the algorithm. And yet, because of this adapted nature, the accuracy of these results is fairly high, since the mesh is adapting itself to the results and ensuring that the flow variables are as accurate as they can be at all locations within our computational domain here. So let's pause that. So that's a quick overview of how you run a simulation. Like I said, at any time you can reset your simulation by clicking on the X and restart it if you want. Of course, you're going to calculate exactly the same thing if you hadn't changed anything, but maybe we changed the flow, maybe we changed the viscosity or something, or maybe we loaded a different mesh. Let me just for fun load a different mesh, and you can simulate that. And there you go. So now we're solving a different application fairly easily by just working with the interface here. So now we're doing airflow past the airfoil, a wing, at similar Reynolds number as we were doing the cylinder. So that's quickly how you run a simulation. You can run a simulation using these controls. You can play it back using these controls. So it's a fairly easy interface, and students should be able to kind of get a handle of this interface and use it effectively very quickly. So that's before we wrap up. Let's go back to our cylinder. Let's load that and rerun the simulation. There we go. So there's, of course, tons of things we're going to do with visualization. That's going to be the topic of part 5 of the tutorial. We're going to cover all of these visualization controls. So in this part 4, we said how do you run a simulation, how do you reset a simulation, and how do you play back the results. So hopefully it all makes sense and is easy to use. So we'll talk about visualization in part 5, which is the next tutorial. So we'll see you there. Thank you.